Yeah, not the Incredible Hulk, but the, who recognizes it? Yeah, the Thing from the Fantastic Four. I saw it at a thrift store and go, I'm getting that for a demo. And you guys will be the first ones to see it being used here at the department. Some professors, how should I delicately put this? It's too childish for them, but not me. Oh, we'll use it. We're starting chapter 6 on momentum. And do I pay for it? I'm in charge of it all, yes. So I manage it, fix them, buy them, replace, set up, take down. So yeah, I got that one. If you guys got any ideas, let me know. I love, though, when you can have the balance between high-tech stuff that you just can't show in another way, or you can't get yourself. But then when toys, something simple can teach the same concept. So some people relate to it differently. So we got a good mix back there. On that vein, the Thing, I thought this would be a good time to briefly discuss your superhero paper, because you've had plenty of time to read the instructions by now. So those of you that don't know what I'm talking about can go read that. But I wanted to tell you a little more. It's not a long paper. It'll be a couple pages, 700 to 1,000 words, I think I said, which sounds long at first, but trust me, once you start trying to meet these points, most people find they have to cut stuff that are actually trying. I tried to make it fun. So it's designing your own superhero. You can come up with any physics principle you want. You have to base it on some fundamental principle. We're going to cover several this semester, but we can't cover all of them. You can address things that we don't cover in this semester. Or if we haven't gotten to it yet, but we will, that's fine. You can go ahead and cover it. Your textbook can help explain those, and there'll be a work cited, so you'll reference things. You can ask me questions, obviously. Also, your superhero, it's not all just that this person has to follow the laws of physics to be able to do it. They can break the laws of physics as long as you explain why. The core behind this whole paper is to show me that you've learned some physics principle. And so you either apply it to a superhero that uses it to their advantage or breaks it, but you can address why because you know exactly how the physics principle is supposed to work and why it breaks it. Does that make sense? You'll just be justifying. So you'll have to pick an idea, a fundamental principle, design your own superhero around it, give them a little backstory, and explain the physics of how they would use it or not. I feel I laid it out pretty clear with a scoring rubric on how much points each would be. Things many students overlook. There are 3 deadlines for the paper that I've instigated. The first one is your idea submission. You can, your idea, you must inform me of your superhero's name, fundamental power, and a list of the majority of your sources. I've started that because, well, I'll be honest, most of you are going to wait till the week before or the weekend before to do this. And your papers aren't as good. So, or you have a lame idea that I could have nixed from the get-go so you didn't waste your time. So that is due any time up through March 13th. And these are listed in the instructions and on the calendar in WebAssign, the PDF version. So up through March 13th. So you have a little over a month to just come up with your idea. Let me know what you're thinking. You don't need all your sources, but I want to see that you've actually thought about it. And said, yeah, this might be good. Well, did you look? Did you find some sources that could work for you? Even if you change them, that's okay. So that should be easy, just coming up with the idea. That way you have time to mull it over and think about it. The next deadline will be a rough draft submission. I'm going to ask you to write it up. It's not your final paper, but I want you to have it written up and peer-reviewed. Meaning, the easiest, and what most people do is, I don't know, you're sitting next to each other, maybe you're friends by now. You'd write a paper and she'd write a paper, and you'd swap so that you would critique hers and vice versa. And then you would sign it and come to me and say, yeah, we did this. And I just give you credit. It's to give yourselves feedback on your paper. Also, if you read someone else's, it's been an eye-opening to a lot of my past students that, oh, that's how they're doing it. I didn't think of doing it. I like that. Or you see, well, they messed up there and there. I feel good about mine. But you can share that with each other. And hopefully your papers will be better for it. That is due in April, beginning of April. A week before you have to turn in your final paper, which is the final deadline. Now you can do any of this before those deadlines. So the deadlines is the last time you have. So you got to come up with an idea. Let me know. Write some rough draft and get it, just peer review it with each other. Or someone else, that's fine. And then you'll turn in the final. So you have till April 8th to get all this done. But if you haven't been paying attention, this is going on through the semester behind the scenes. Any questions? Those of you read it or now or anything?
You haven't specified how many sources you want?
I didn't specify the number, no. Sufficient to know you research something. Typically, it's anywhere from, I don't know, 3 to, I've seen like a dozen. You don't need a dozen. That's fine. If you just have one, if it's a really good source, it might all be there. I find most people, though, tend to look up things and find some information they can use in at least a handful. Your works cited, too, I explained that in here, but since it came up, actually, I probably have most of the explanation about the sources. It's mainly just use sources, but don't plagiarize. If you used it, reference it. And the way you reference it, I don't mind the format. We don't have to do, this isn't an English class, so you don't have to have it a semicolon here and underline that. As long as you give me enough information so I can go exactly where you were at. On a web page, so far down, in a textbook, this page, so I could go there and see what you saw and not have to figure out where you're at. That's all I require with your works cited. Other question? I hope this will be fun for you. My main impetus for this is, I've told you before, when you try to explain physics yourself instead of just answering questions, you learn a lot more. Most people have told me they've enjoyed doing this, so I hope you will too. You might as well pick something you're interested in, have fun with it. So, if you got questions as they go along, let me know. All right, you ready for momentum then? Get the ball rolling. Bad physics pun. Yeah, thanks. He's smiling. Okay. You guys have heard of momentum, I bet, right? And one of the students has talked to me outside of class. He's already thinking about it. He just didn't realize it. So we labeled it what it was, and now we can discuss it more. Momentum is usually denoted with a P in physics. I don't know why. And I like to think of it as, let me ask you this before I give you the answer. Because to show you, you guys know a lot of this. If you just stop and think. Again, this class, you can't just memorize things and when questions pop up, what was I supposed to use? Oh, what did I memorize? It's usually you have to internalize what we learned and apply it. It's usually you can't answer a question in just one step. So, to give you an example in your practical everyday life, which would hurt more? A big truck that runs into you? Or a little Timmy riding on his tricycle? The truck? Who else thinks the truck? Anybody think the tricycle? It depends on velocity. Okay. What if they're going the same speed and they hit you? The truck? Now, what if the truck was going really slowly and the tricycle was going super, super fast?
Depend.
What's that?
It would depend
Depend on what?
on like the mass-velocity ratio.
The mass and the velocity. See, your guts are right. That's momentum. Momentum is mass times velocity. Because we've been talking thus far about mass and a measurement of inertia and resistance to change. And the more mass it is, the more it's going to resist. So something that's heavier would be harder to stop just because it's more massive. If it's already moving, you have to apply a force to stop it, it's going to resist that. Or vice versa. You try to move it. Something big is hard to get going in the first place because of its inertia. So that's this part right here. So I like to think of momentum, though, as inertia in motion. Because it matters how fast it's moving as well. And that was what my example was trying to illuminate. A Mack truck that just kind of bumps into you. Yeah, there's a lot of inertia there. You're going to feel it. But if it's going slowly, meh. Whereas little Timmy on his tricycle moving at the speed of light is going to cause a lot more damage. You just know innately that that's going to be harder to stop. That's because little Timmy might not have as much mass, but if he's moving fast enough, he could have more momentum than the big truck moving slowly. So you can play this game again. Let's say they have the same momentum. Say both the truck and the tricycle have the same momentum. Well, the truck has a big mass, and the tricycle has a little mass. So you can see, in order to have the same momentum, the truck would have to be moving slowly, and the tricycle would have to be moving quickly to keep that product the same. That's momentum, inertia in motion. It's a lot like inertia. It's just inertia is when something's at rest or in motion. Momentum, clearly, it's only if you're in motion. Because if you're not moving, what's your momentum? There's your guide to thinking. I try to do them both conceptually and when there's equations, because some people relate differently. So if you don't know what I'm talking about conceptually, when I say, if you're not moving, what's your momentum? Well, what if you just plug in a 0 there? What do you get? 0. So you have no momentum if you're not moving. All right. Now, any questions about that? Yeah.
One thing, you are talking about the truck and the tricycle. If they are riding parallel to each other, you are not talking about a truck and a tricycle going to crash to each other.
No, we're going to do collisions next class when they run into each other. I was just talking about if this, my initial example was if the truck ran into me or the tricycle ran into me, separate instances, then it depends on their momentum which one will actually probably hurt me more. Because the one with more momentum would be harder for me to stop and exert more force on me. And it's not anymore just about mass. Because if the truck is moving slowly enough, it might not have as much momentum if the tricycle were moving super, super, super fast. Yeah?
Does the force come into play when you're trying to change the velocity?
Yeah, the force does come into play when you're changing the velocity, just like before. Yeah, that's what I'm doing next. See, Eddie, you're always thinking. Let me preface it with, at this point, you're at least mostly familiar with this. I mean, you should be, but I don't know how comfortable you feel with it yet. The acceleration, we've discussed that. But there's another way to define acceleration. A change in velocity, right? We've said in order to have an acceleration, you got to exert a force on something, a net force, or it won't be accelerating. And if it's not accelerating, this is 0, there'd be no change in velocity. I think you got that if you want to make something move, you have to overcome its inertia, so you have to apply a force to it. That force will cause that mass to accelerate and change its velocity, whether it was at 0 to something or whatever it was to something else. It'll change. That requires a force. So I'm just going to combine these two. That equals acceleration. That equals acceleration. So they equal each other, and I'll just bring the t over here, multiply both sides by t, and I'll multiply both sides by m, and we'll do it that way. This has another name. It's called impulse, and this one's less familiar to most folks. Impulse is a force applied for a certain amount of time. Up till now, we've just talked about the force. But it takes a certain amount of time to apply that force. We're going to start considering that now. And what's that going to do? It's going to cause a change in the momentum. So you can think of this as a change in momentum. Those are all the same thing. Impulse is force times time, or a change in mv, or a change in momentum.
The impulse can be a change in momentum.
Impulse is a change in momentum. Now I want to emphasize that. Impulse and momentum are different things. Momentum is inertia in motion. It's just mass times velocity. Impulse is a change in momentum. If momentum's not changing, there's no impulse. Yes? Yes, the relationship between acceleration and velocity. Acceleration is a change in velocity. Impulse is a change in momentum. Now, for most practical applications, and what we'll be dealing with in this class is usually in order for the momentum to change, it'll be the velocity that's changing. There can be instances, though, where the mass is changing. Thus, we'd have a change in momentum. I can think of one example right now. Can you think of one? Can you think of something where something's happening and where the mass is changing? Hey, and that was the one I was thinking of, the rocket. It starts out with so much fuel, but as it uses it up, its mass decreases. So that causes a change in momentum as it uses up the fuel. Good. Now there's maybe a train car as it comes by and gets filled up with water or coal. Its mass increases as it's moving. That would be a change in momentum. But again, for most cases, this will be because of a change in velocity. So again, I can't emphasize this enough because it throws people off. Impulse is not momentum, but it is a change in momentum. And in order to create that change, just like before, when we had a change in motion, you had to apply a force. To create a change in momentum, you have to apply a force for a certain amount of time. And we're going to play more with this. That can explain many things. Let's do one. Let's do this one. It's always good when you can have marshmallows, so they're old and crunchy, but they actually work better for this then. So I have two PVC rods. They're just hollow so that I can put one in, maybe a smaller one. Put them in here and shoot them out. Something that actually fits. Okay, so I'm going to put one right here next to my mouth and blow. But I'm going to put in the other pipe, I'm going to put one on the far end and blow. So there'll be one close and one far. And I'm going to apply the same push to both. Like that. What do you think will happen? The one that's closer to my mouth will go farther? Why?
Because by the time the air pressure gets to the end of the tube, it's going to have dissipated get farther from the mouth.
By the time the marshmallow gets to the end, the pressure will be dissipated?
No, like on the other one,
Oh, the other one. The one that starts far away?
Larger volume, and you're putting the same amount of air into that bigger volume, therefore there's going to be less pressure on the head.
Bigger volume, so less pressure because it spreads out. Because I'm trying to pressurize more of the whole volume. Where the one that's up here, I'm just trying to pressurize before it. Okay, good. Any other thoughts? Oh, I know you guys are. I know you're thinking. Come on.
Are you going to blow both ends at the same time?
Yep. That way, I'm trying to be uniform and consistent. Yeah. I can do them separate, but then you might think I blew harder or something. No, good. Nobody giggled. I don't blow hard. Okay.
On the one that's closer to you, it goes through the pipe.
The one that's closer to me, it goes through the pipe.
Build speed.
It builds speed. It's going to change its velocity, and you only get a change in velocity when what's applied? A force. The one that's at the far end, I'll apply a force to it, but it leaves. And so if I keep blowing, it's not feeling that force because it's left. That's the idea. The one close feels a force for a longer amount of time. The one that's far away only feels my force for a brief moment. Now let's look back at this equation. If I apply the same force to both of them, but one has a bigger amount of time, that'll be the bigger product, right? So the one that I apply the force to for more time, that will provide a larger impulse. So the one at the far end will feel a larger impulse. An impulse is a change in momentum. So it will also receive a greater change in its momentum. I'm not going to change the mass of the marshmallows. And they both start at 0 meters per second. So the only way they can change is by one of them going faster than the other. Now that you know everything that's going to happen, we can do it. No surprise anymore. You guys figured it out. All right. And you can see one just went, and that was the one that was right at the end. We need a slow motion camera so you can tell, right? But here's the one right next to my mouth. Here's the one at the end. Yeah. It still feels a force, it wasn't able to feel the force for as much time. So it couldn't receive as large an impulse, does not receive as great a change in momentum, doesn't get going as fast. And if it doesn't go as fast, it doesn't cover as much distance in time. We've done velocity now. Look at you, see, you're 4 or 5 step process physicist now. Oh, you don't want to eat it? I don't either now. So there's a feature to that, practical application. Cannon. You could have a short cannon or a long cannon. If you could sustain the force, the explosion, for a longer time, yeah, that alone could increase the impulse because there's more time and thus create a bigger change in momentum and make it go faster. To a point, there'll be a resistance in there the longer and longer you make the barrel, but let's look at it another way. I need a volunteer, though. Actually, I'm going to need 3 volunteers for this one, or I can't do it. 1, anybody fancy themselves as a pitcher? Phil, you like throwing things? Nobody? Somebody like to throw something? All right, you're the thrower. You're the thrower? Did you say that? Or?
I'll do whatever. You can throw.
All right, you throw. You're a holder. I need one more holder. We're going to catch what they throw with the sheet. Thank you. All right, the holders come over here. You might want to move over here. Nothing else so you can see. Let's see. Let's do it this way. All right, hold that with your right hand. Hold that with your left hand. Grab the other corner with your other hand. You're the net. All right, hold that one up as high as you can. Hold it fairly tight. He's going to throw into you, so let's get perpendicular to him. That works. Hold this corner. And then you hold that up because in theory it'll land here and maybe we can catch it.
Oh, gotcha.
So you'll hold that up, and you get to throw an egg.
Boiled?
No, it's juicy. We bought it on January 24th. Now, your job is to throw it into that sheet and make it break, the egg.
What if it breaks in my hand before it gets to the sheet?
Don't squeeze it that hard. Gotta coddle it.
What if I can throw so hard that it just, the force?
Then we'll all applaud, and I'll give you a second egg. Now, if you want to get closer because you think you'll miss, that'd be fine. Pretty much the only thing they're worried about is don't hit them. If you miss the sheet altogether, which has happened several times, we'll survive, but don't hit them. So, you know what? No, I'm just kidding. All right, I want you to throw it hard and see if you can get the egg to break.
Whenever?
You got it. Whoa, that was good. Did it survive? Yeah, you want another try? Think you can throw it faster?
Yeah.
Okay, come on, make it break. I can wash the sheet. Whoa! All right. I think that proved the point here. Thank you guys very much. Give them a hand. They can take a seat. All right. Why did it not break? I have never seen anybody be able to throw it at the sheet and break it, ever.
It's a real egg.
Yes. Dissipated the force.
The blanket, the sheet gave.
The sheet gave. Good. See, you know this. Your intuition's right. I bet all of you are thinking that. It's the kind of cushions. Now apply it to what we just talked about with impulse.
Did the time it took to hit the sheet was slower than the time before?
The time it took to hit the sheet. If the sheet gives, that increases the amount of time of the collision, of the impact. So he throws this at some super velocity, 100 miles an hour, right? No. So it's coming in with momentum, correct? It's got an initial velocity and mass. It's inertia in motion. In order to stop it, the sheet has to apply a force onto the egg to slow it down, right? Well, it can do that two ways. It can apply a really large force for a short time, or less force for more time. Let me write that. So it's going to have a change in momentum. Its velocity is changing in this case. Yes? It's going to come to a stop, whether it hits the brick wall or a sheet. It goes from 100 miles an hour to 0. So the change in momentum is constant in this case. Do you agree? That's impulse. Impulse and change in momentum, same thing. How do we get that? We exert a force over time. Well, it can either be a big force for a short time or a little force for a big time. And the sheet did more of this. Because it cushioned, your terms, dissipated the force. It stretched. Well, that increased the time of impact that the force was being applied. So you can have the same change in momentum with less force. You could have the same change here with more force, but it wouldn't take as long.
That's how airbags work.
Exactly why airbags work. Yeah. The airbag helps cushion your collision if it has to happen. Laura, your airbag didn't go off, did it? Good. You can hit the steering wheel or the dashboard or the windshield. Do you think they're going to be very giving? No. They're going to stop you quickly. So you'll exert a force on them. They'll exert the exact same force in the opposite direction back on you, and it'll be a big force. Break bones. The airbag, even though it's actually really quite rigid, it does give. And that increases the time of impact ever so slightly, but enough to make the force small enough that maybe you actually survive. Airbags are great. Also, why you should wear a helmet and pads when you're doing wonderfully dangerous, sporting activities. Most people think, oh, I'm fine, I'm fine. But if you crash, the number one injury is head injuries because people aren't wearing a helmet. If you wear a helmet with that little bit of cushion, could save your brain, you know. Yeah. Is that the same thing with a parachute? It does keep you in the air longer. That's true. But it's more with the, you got your weight down, and if you had nothing retarding your motion, you're going to hit the ground harder because you have a mass and you're going to be going a certain speed. So you're going to come to the ground with a certain momentum. The ground is going to stop you, right? One way or another. So when you hit the ground, you're going to have a change in momentum. It'll slow you down. That's going to require a force for a certain amount of time. So the parachute doesn't help with that time. But it can decrease how fast you come in at, so that you'd have less momentum hitting the ground, coming into the ground, which means there's a less change needed, less impulse, less force needed to stop you in the first place. A trampoline would, yes. You can hit the ground, and the ground can stop you like that. Or you can hit a trampoline, and it gives. And so it requires less force because it can exert it for a little longer of time. Yeah, and it's much more comfortable to land on a trampoline. Very good. The ski sports in Park City where they train, I see them jump off to practice their flips, and they land in a swimming pool. But if you notice, it like triggers something. While they're in the air, they start percolating air up through the bubbles, through the water. So it's like this air-water mixture to make it softer. It's like a pad. So it extends the time of the collision there when they hit the water, and so the force they feel is less. If they were to hit the water that was still, it would stop them faster, and it would hurt more, and they'd break things. I always like watching the bubbles come up. So, that's where the thing comes in. That's why I had to get it. So, would you ever do this with your bare fist? I hope not. But the padding in here, there's enough of a cushion that I'm coming in with a certain velocity. Whether I do it, I guess I should do it where you guys can see me, like that, or like this. I can come in with the same momentum. It's going to be the same change in momentum. It's going to stop my fist. So it's going to require the same impulse to stop me. Do I want to do that quickly or slowly? Slowly, so I feel less force. That's what pads are for. Oh, it's got a little battery and speaker. I think it's just trying to make funny sounds the thing would do, like picture a little boy, cool. It's just for effect. This is just, there's a sensor in there. It can actually detect the impulse force, and that triggers it. And it doesn't take much. So see, maybe if you were clueless before, you can have some idea of how you can easily relate this physics stuff to superheroes, because it's all over the place with superheroes. All right. I want to remind you that Newton's third law comes into play a lot here. Because when two things collide, when I hit the wall, when the egg hit the sheet, when you parachute down into the ground or not, two things are hitting. How does the force compare on the two objects? They're the same. That's Newton's third law. The egg hits the sheet exerts an equal an opposite force back on the egg. Up till now, we thought, okay, the force is the same. You have a little egg accelerating a lot, and you have a bigger sheet that doesn't accelerate much. But they felt the same force. Well, now you can throw in the time. It's going to cause a change in momentum. That force is applied for a certain amount of time. It provides a certain impulse, a change in momentum. But it's the same force on each object. But it's not necessary. Well, yeah. So how do you think the impulse compares for both objects? If the force is the same, how does the impulse compare? So conceptually, we're not there yet. Let's look at the formula. Here's impulse. So I don't have to put the board down. And there's the force. Okay. If it feels the same force, and two objects are hitting each other, and the force is only applied when they're in contact, this one feels this force, this one feels this force, are they in contact for the same amount of time? I mean, if this one comes off, are they exerting forces on each other anymore? So how do you think the times compare? They're the same. If we're talking about two things running into each other, the force we know is equal and opposite, but now you know too, the time is the same because it's those two objects hitting each other. It's while they're in contact. So this one is in contact with this one for the same amount of time, this one's in contact with this one. Does that make sense? Okay. So if these are the same, what else is the same? Impulse. They're going to both experience the exact same change in momentum. They might have different momentums, but the change will be the same for two things colliding because they're feeling the same force for the same amount of time because they're the two involved. This is force times time. This is change in momentum. We're not changing the mass, we're changing the velocity, which is one way to change the momentum. These are all equal. And yes, this is impulse. Impulse is force times time. It is a change in momentum. And again, it's not momentum. So we might have homework problems where the momentum is different, but the change in momentum can be the same. Yeah?
So you're saying like when you throw the egg at the sheet, like the sheet's not coming back at the egg. Because, well, when you're going back to the airbag example, the airbag's being like shot out and then collide with the body going towards it. So I'm just trying to figure out how those could be the same. Or maybe they aren't. Like when the airbag like is colliding with the body, like it's being shot out and having a great momentum like force towards the person. So it's not like it's cushioning, but I feel like it's also like putting a lot more force on the body.
Good insight. To sum up, how does the egg collision with the sheet compare to the running into an airbag? And they aren't exactly the same. The point that was the same is that both the airbag and the sheet extend the time of collision. So there could be less force involved. What's different, though, is the sheet wasn't moving initially. So what was its initial momentum of the sheet? Zero. No velocity, no momentum. The egg had momentum though, right? It had a mass and was moving fast. The total momentum of the system, we're going to start talking about conservation of momentum. And for the system, it's always conserved. So the egg had momentum, and the sheet has none. So the total momentum was whatever this equaled. For the airbag, you're moving forward, so you have momentum. The airbag actually shoots out at you, so it actually has momentum in the opposite direction. Momentum's a vector because velocity is a vector. It matters which way you're changing your momentum. And so the total momentum is the addition of both of them. One's positive, one's negative. So there'll be like a net momentum, the total momentum. And that always has to stay the same. And that will affect that force as well needed. I'm going to bring in an air track and do collisions a lot Friday and work some examples of these. When they bounce off each other, when one's bigger than the other, if one wasn't moving, if they stick to each other, and we'll play that game. Let's do this collision while I'm at it. You drop a basketball, let's say from this height. Where do you think it'll rebound back up to? How high? 75%? As high? 50, 60? All right, let's see. So, lame. The idea is here, it loses some energy. And we're going to get into that more.
Also because
It's transferred to a different form, and the ball no longer has that energy, so it doesn't come back up as high. But it does rebound. Some of the energy comes back. There's a collision with the floor. You can do a similar thing with the tennis ball. It's an old tennis ball, so it's not as bouncy. But something neat can happen if you put them together. What do you think will happen if I drop it now? Big one will push the little one? They'll settle at the bottom? The big one will go higher than it did before? What's going to happen is, let's see, this one's going to hit the floor first, and then it's going to rebound on its way back up while this one's still coming down, microscopically. And so essentially these are going to have a collision vertically. And we'll see what happens. Well, I'm guessing this one's more massive. It has more inertia. And if they're going the same speed, see, they're going the same speed, who has more momentum? The ball. Momentum is mass times velocity. If they're going the same velocity, this one has more mass, it has more momentum. When they collide, they can transfer momentum. The total will still be the same. Again, we'll discuss that more. But this one has more momentum initially than this one. Let's try it this way. What do you think? So they collide. Momentum is transferred. This has more than this one. It transfers some to it, and this now has more momentum than it started with. If that's true, if this guy has more momentum than he started with, what do you think happens to this guy's momentum? It loses some, it goes down. Watch how high this bounces this time. Don't watch this one. Watch the basketball. Except for when it's going to hit you. Did you notice it didn't bounce as high as before? So you could see that it didn't have as much momentum after the collision with the tennis ball. Now, should we get exciting? What do you think will happen?
What is that?
That's the egg. Should we try it? Yeah, what do you think will happen? It'll break? When will it break? When it hits the basketball? All right. Does anybody think it won't break? Okay. A couple on the front row thought, if it doesn't break, where's it going to go? I'm not sure. So are you guys paying attention? Are you going to catch it for me if it doesn't break? Okay, you ready? I'll try to drop it straight so it goes up straight, but you never know. It didn't break. Which tells us what? What's that tell us? These collided. And then boom! Down here they collided. Go for it.
The force of the resistance and the air was less, so it could bounce away than the force it would take to smash it into the ball.
Force of the air resistance was less than the force smashing into the ball?
So it went into the air instead of smashing the ball.
Went into the air. Close. There's a lot of truth to that. Who wants to add to it? I heard something over here, and I forgot what it was, though.
Well, it was like cushioning from the basketball.
Yeah, these aren't rigid. Well, this is less rigid than this. Yeah, this gives. kind of like the sheet or an airbag. It must have gave enough to extend the time of the collision sufficiently that both felt not as much force. It wasn't enough force to break the egg. Now, how many of you think I've been using a fake egg this whole time? Was the time of collision long enough? No. So in that case, it felt too much force. More force than the egg could push back. And so it broke. So yeah, it was a real egg this whole time. Yeah.
So what if you were to use like two basketballs or two tennis balls so they're the same weight?
If they were the same thing, yeah. Two basketballs. What do you think? Gee, somebody stole my second one, right? We'll go grab one right now. What?
I said they'd cancel each other out. They felt there would be some transfer of energy to the floor.
Yeah, well, I'm going to save it. You think about it. But the idea is they'd both have the same momentum, wouldn't they? Because they're the same mass going at the same speed. So it's like two identical objects coming and colliding and bouncing off. If they both have the exact same momentum to start with, do you think one will come out faster than the other? We'll see it tomorrow. I want to see, what do we got, 4 minutes? Okay, here's a squishy ball. I call it a splat ball. And if it makes a collision with the board. I use this just to emphasize we're going to be talking about collisions, and it's the forces involved with the collisions. In other words, this has weight, right? We got that down. The force the floor is feeling right now is its weight. What force does the floor feel now? Is it its weight? No, it's moving. It's got momentum. You know this because would you rather me just set this on your foot or throw it on your foot? If I threw it, you know it would hurt more. It's because it's coming in with momentum, and that takes force to stop, in addition to its weight. So this collision is important, and they generally happen quickly. So I wanted to do this. Let's throw it slowly. And you can see that it's spread out. You know, high-speed cameras are where they come in great now. It's and then back. That's the time of the collision while the force is being applied. What if I give it more initial momentum? If it's coming in with more momentum, it's still going to come to a stop before it rebounds. So the change in momentum will be greater. Change in momentum is the same thing as what? Impulse. So impulse will be greater if I throw it faster. And impulse, what's it going to take to I'm babbling. It's going to take something to stop this, a force for a certain amount of time. Let's see what happens. It's a good throw, but make it more obvious. Wow, that was bad. Okay. There we go. So that one you can see spread out further. The time of impact was probably different for that one than this one. So the force felt was different as well. I'll save that for next time. Any questions? I had a couple clicker questions I'd probably do with this, so we'll probably start with that next time. Do some more collisions. Finish chapter 6 and have a weekend. So see you Friday.